Dear all, welcome to the series of lectures on solar energy fundamentals. The aim of these lectures is to disseminate the knowledge among the solar energy experts working in the industry or undergraduate or graduate students taking a course on the subject in any university or college across the globe. The goal of these lectures is to familiarize to all with the basic principles of solar energy so that they can use this information to determine the availability of solar radiation in any location on planet Earth. With this information, they could design, develop and evaluate solar device efficacy. This lecture includes all general information about the Sun and Earth, which is a required piece of information. The points to be discussed in this lecture are the Sun, physical feature of the Sun, nuclear fusion reaction, energy generated in the Sun during fusion reaction, some facts about the Sun, then the Earth planet, latitude and longitudes and their significance, and at the end of the lecture we'll discuss about the Earth atmosphere and its different layers: troposphere, stratosphere, mesosphere and thermosphere. Now we will learn about the Sun. Sun is a medium-sized yellow star that may be considered as a sphere of intensely hot gaseous matter with an average diameter of 1.39 into 10 raised to the power 9 meter at an average distance of 1.495 into 10 raised to the power 11 meter or 1 astronomical unit from the Earth. Interestingly, Sun is 109 times the size of the Earth, and other interesting facts is it so large that you could fit 1.3 million Earth inside the Sun, or to cover entire surface of the Sun by flattening the Earth you need 11,990 flattened disks equivalent to the size of the Earth's surface. Astronomer thinks that the Sun formed by the coalesced from a cloud of gas and dust around 4.59 billion years ago, and these gases and cloud dust come closer, creating a tremendously high density and pressure of magnitude 10 raised to the power 5 kg per cubic meter and 1 billion atmospheric pressure respectively at its center. It is largest celestial body of the solar system, owing 99.68% of the total mass of the solar system, and the second largest planet of the solar system is the Jupiter, which consists of 0.2% of the mass of the solar system, and planets like Earth are consisting of fractions of mass of the solar system. The 74% of the Sun mass comes from the hydrogen with 24% helium, and remaining 2% includes the traces of the iron, nickel, oxygen and other elements. Like other planets, it also rotates at its own axis from west to east, and to complete one rotation it takes about 4 week time. Since it is hottest body of the solar system, so the estimated temperature at its center varies between 8 into 10 raised to power 6 to 40 into 10 raised to power 6 Kelvin, and mean temperature is about 1.5 billion Kelvin. At such a high temperature, it continuously releases energy due to fusion reaction. However, it is worth noting that the temperature of the Sun surface is around 6000 Kelvin. Now we will talk about the nuclear fusion reactions that takes place inside the Sun, involving the fusion of two lighter atoms to produce a single higher atom, and due to this process the Sun continuously emits heat. Since the Sun is a sphere mainly made of the compressed hydrogen and helium gases, here inside the Sun two lighter hydrogen atoms come together to form the single nucleus of the heavier helium. Each hydrogen atom has a positively charged proton in their nuclei. This condition raises questions on the validity of the reaction because positively charged protons in the nuclei of the hydrogen atom will create a repulsive force instead of attractive, and hence the condition do not favor the fusion of the atoms. It means to fuse like charged hydrogen atoms, it needs to overcome the repulsive force between the hydrogen atoms. The repulsive force can be overcome in one of two ways, either by exerting pressure to the area where two hydrogen atoms with like charges should fuse together by pushing them towards one another, or alternatively by increasing the temperature of the region where the electromagnetic force between the hydrogen atoms may be reduced. Fortunately, the Sun has both of them. Dense hydrogen plasma makes up the Sun's core. The hydrogen atoms present in the core move around with tremendous force, but they avoid colliding with one another because positive charges repel one another. This means that when two hydrogen nuclei with positively charged proton try to approach, the repulsive force keep them apart. These positively charged hydrogen atoms collide only when the enormous force of more than a billion times of atmospheric pressure that is present in the core is applied on them. The nuclear force comes into play when these hydrogen atoms comes nearer under the influence of the external pressure and fuse into a single nucleus. Some weird things happen as a result of this phenomena. One proton from the two that were fused emits two tiny particles. One of these is a very small particle called neutrino, which emits from the core and travels at almost the speed of light before ejecting energy into the space and never being seen again. The second particle that the fused proton emits is an anti-electron. An antimatter electron has a positive charge instead of usual negative charge that an electron carries. Because it carries a positive charge, the fused proton that created this anti-electron particle loses its charge and transforms into the neutron. So this fusion reaction causes a process known as the beta plus decay, which produces neutrons in helium. The collision and subsequent fusion of two hydrogen nuclei has resulted in a single nucleus having one proton and one neutron. This new nucleus is known as deuterium, which is hydrogen isotope. This deuterium nucleus continue to bounce around the Sun's center with all other particles before colliding with another proton and fusing. The fusing of deuterium and hydrogen nuclei results in the formation of a new nuclei with two protons and one neutron. This new nucleus makes up of helium-3, the lightest type of helium. During the formation of helium-3, powerful gamma rays are emitted. This energy is absorbed by the Sun's plasma and increases the core temperature. This helium-3 nucleus bounces around in concentrated plasma until it collides and combines with another helium-3 nucleus. When two nucleus of 6 particles, 4 proton and 2 neutron fuse to produce a new nucleus, the 2 protons are ejected by force from the newly formed nucleus. The ejection of proton produces gamma rays which create extremely high heat. These two expelled protons are reused in the fusion process, resulting in the continuation of fusion process in the Sun. The particle formed from 2 proton and 2 neutron is known as helium-4. Helium-4 is the final result of the fusion reaction that has occurred. 4 hydrogen atoms with 4 electrons and 4 protons are fused during the fusion reaction in the creation of helium-4. When helium-4 has only 2 electrons, the question of what happened to the remaining of 2 electrons emerges. To understand this, we have to consider the process by which 2 hydrogen atoms fuse to form 2 anti-electrons. During helium-4 formation, the leftover 2 electrons collide with anti-electrons, releasing energy and disappear in the environment forever. After knowing that how fusion reaction take place inside the sun, it would be interesting to calculate the energy generated during this process. We saw in previous slide that 4 hydrogen atom fuses together to form single helium atom. This newly formed helium atom has 0.65% lesser mass than that of combined mass of 4 fused hydrogen atom. This loss of mass gets converted into energy, and what amount of the energy released during the fusion reaction can be calculated by using the famous Einstein equation E equal to delta mc square, where delta m is mass lost during the fusion of hydrogen atom and form helium atom, where c is the velocity of light, which is equal to 3 into 10 raised to the power 8 meter per second. In order to obtain the loss of mass, first we see mass of single hydrogen atom is equal to 1.6736 into 10 raised to the power minus 27 kg, and 4 hydrogen atom together have mass equal to 6.693 into 10 raised to the power minus 27 kg. After the fusion reaction, the newly formed helium atom has mass equal to 6.645 into 10 raised to the power minus 27 kg. Difference in the mass of 4 fused hydrogen atoms and newly formed helium atom is equal to 4.8 into 10 raised to the power minus 29 kg. Place the value of mass lost during the fusion process and the value of the velocity of light c and their product together result into the 4.32 into 10 raised to the power minus 12 joules of energy generated during the single fusion reaction. Around 600 million tons of hydrogen converted into helium every second inside the core, which attain approximately 14 million Kelvin temperature at the core. The 90% of the total energy generated by the sun happen in its core. From this data, one can imagine the amount of energy generated every second. One study showed that this value is about 3.86 into 10 raised to the power 26 joules per second. If we look at the exterior feature of the sun, the main inner layer of the sun are core, radiative zone, convection zone, and the outer layer or the surface is called the photosphere. The sun do not have a real outer edge like our planet Earth because it is made up of gases only. So the outer boundary is roughly defined as the radius where the sun becomes optically opaque. If we designate the radius of the sun by the symbol capital R, then the area at the center ranging from 0 to 0.23 times to the radii of the sun is termed as core, where 90% of the energy generated by fusion reaction, and also this region is so densely packed that 40% of the total mass of the sun accumulated in this region comprises 1.2% of the total volume of the sun. This region has conducive environment to favor the fusion of hydrogen atom because of 1.5 billion atmospheric pressure in the core helps in neutralizing the repulsive effect of two like charged hydrogen atom and fuse them together to form one deuterium atom. The core is followed by radiative zone ranging from 0.23 times of radii of the sun to 0.70 times to the radii of the sun. The photon carrying energy in the core propagate towards radiative zone. While their propagation, photon collides with the hydrogen and helium ion and get absorbed and again get emitted. Also, due to very high density of the core region, the traveling of photon from core to the top of the radiative zone can take 10,000 years to hundreds of thousands of years. Sun is very large and complicated celestial body, and it is very difficult to know all about it in a very few slides. So in this slide also have few more facts about the sun. Radiative zone is the very dense part of the sun. The photon generated to fusion reaction carry energy from core to radiative zone, and while reaching to radiative zone they take 10,000 to 100,000 of years. Above the radiative zone is the convective zone, which spans the outer 30% of the sun's interior. Sun radiates heat at the rate of 3.8 into 10 raised to power 26 watt. The convection zone begins when the temperature drops to 80 times to that of radiative zone, which is around 100,000 Kelvin. In the convection zone, energy is transported by the movement of the plasma or the hydrogen and the helium ions. Plasma churns vigorously, transporting heat energy to the surface of the sun through convection. The energy created in the deep core of the sun by nuclear fusion must travel through several layers of the sun before it reaches to the sun's surface. While propagating this energy, it suffers radiative and convection losses. Consequently, the outer surface temperature of the sun, which is reported in many studies to be about 6,000 Kelvin, but for the calculation point of view, sun's black body temperature is considered in literature equal to 5,777 Kelvin. This decrease in temperature from core to outer surface of the sun is due to heat dissipation, as already been told, which is about 3.8 into 10 raised to power 26 watt. This lost heat energy is distributed in the entire solar system, including our Earth. The other planet receive the amount of this energy depending on the size and distance from the sun. Above the surface of the sun is a region of the atmosphere called the chromosphere, where the temperature can reach 10,000 Kelvin, and interestingly, at more distant region called corona, which comprises the volume even larger than the sun itself, has temperature around 100,000 Kelvin. We know that the sun has a spherical shape and it is placed in the middle of the solar system, and other planets revolve around it. The energy radiated by the sun, part of it is received by the earth. The radiated energy received on earth depends on the geometry of the earth and envelope of earth atmosphere surrounding it. The earth has an almost circular shape with a diameter of 1.27 into 10 raised to power 7 meter and revolves once in a year in an elliptical path around the sun. It is inclined at an angle of 23.5 degree and rotate about its own axis. It takes approximately 23 hours and 56 minutes to complete one rotation. The planet receives radiation from the sun that amounts to about 1.7 into 10 raised to power 8. As the earth moves in its elliptical orbit around the sun, we experience two solstices, one in December and the other in June, as well as the two equinox days, one in March and one in September. The winter solstice marks the year's shortest day, while the summer solstice marks the year's longest day in the northern hemisphere. December 22 is the shortest day and June 21 is the longest. The two equinox positions that we experience on March 21 and September 23 cause night and day to be approximately equal in duration when the sun crosses the equator or 0 degree latitude. During the equinox, the sun's declination angle is 0. However, during the summer solstice, it rises to plus 23.5 degree, and during the winter solstice, it falls to minus 23.5 degree. Sign convention for declination angle pertain to the northern hemisphere. For the southern hemisphere, the sign convention will be reversed. The details of the declination angles are covered in subsequent lectures. Perihelion is the position when the distance of the earth and sun is minimum. It is around 1.473 into 10 raised to power 11 meter, whereas aphelion is the position when earth is at a farthest from the sun, which is about 1.521 into 10 raised to power 11 meter. If we see more closely, this shows the variation of 5 million kilometer, and hence for the general calculation point of view, we use the mean distance value of 1.495 into 10 raised to power 11 meter. From the winter solstice, that is December 22, to the first equinox, that is March 21, the Earth moves around the Sun in 89 days. From the second equinox, that is September 23, to winter solstice, it takes 89.8 days. From the March equinox to the summer solstice, or June 21, Earth travels the path in 92.8 days, and from the September equinox position to the summer solstice, it takes 93.6 days. This data certify the fact that Earth takes longer time to travel along the right side of its orbit path than along the left side. Different parts of the Earth's surface receive different amount of sunlight during the daytime and throughout the year. This difference in sunlight received at different locations drive atmospheric circulation. Locations that get more solar energy have more heat and vice versa. From the solar energy subject point of view, it is important to know the exact amount of solar radiation received at a particular location on the Earth for fair assessment of the performance of the solar devices installed at the particular location on the Earth's surface. However, for geographical and various other regions, both the longitude and latitudes are used for GPS as coordinates to pinpoint the specific place on the Earth and also to measure the time of place. Latitude measures the distance from the equator to the north and south pole. The equator is the horizontal circle that cuts through the center of the Earth. The latitudes are other circles that have been drawn on the globe parallel to the equatorial plane and are situated north or south of the equatorial plane. On the globe, all of these parallel circles run east to west. The angle that is subtended between the line connecting the Earth center and the reference point on any of these circles and its shadow on the equatorial plane determines our location on the Earth's surface when we move along these horizontal circles in either the north or the south. The equator is also known as 0 degree latitude because at the equatorial line the angle subtended would be 0. Longitude measures the distance from the prime meridian to the west on Earth. On the half of the vertical circle that passes through the Greenwich, England, is known as the prime meridian, and on the other half that passes through the middle of the Pacific Ocean, it is known as the international dateline. We divide the globe into equal length lines of longitude that alternatively travel east and west of the prime meridian from north pole to south pole. The longitude line is represented anywhere on the surface by the angle formed by the vertical plane through the prime meridian and the reference meridian. Since the person travels along the equator, which is a complete circle of 360 degree, starting from a location on the prime meridian and back to the same point, half of one is 180 degree and 1/4 is 90 degree. In a similar way, any other point on the equator indicates a distinct angular position. The Earth atmosphere was created during the formation of the Earth, when various gases stored within the Earth may have escaped 1 million years ago and gathered around the Earth in the form of greenhouse gases due to its gravitational impact. Ozone, oxygen, nitrogen, carbon dioxide, carbon monoxide, and water vapors are jointly form the greenhouse gases. All of these gases escaped from the Earth and landed above it. The Earth atmosphere is the region above the Earth's surface where these gases settled. The amalgam of these gases together called Earth atmosphere because of its proximity to the Earth. The lower side of the Earth atmosphere is known as the terrestrial region and upper portion is known as extraterrestrial region. The first layer, which is in the vicinity of the Earth's surface, is the troposphere. This is the lowest atmospheric layer. Practically all weather occur in this region. Troposphere begins at the Earth's surface and extend up to 12 km. It contains 80% of total atmospheric mass. The height of the troposphere varies from the equator to the pole. At the equator it is around 12 km high and at the pole it remains 4 km high. The upper layer of the troposphere is called tropopause. As the density of the gases in this layer decreases with the height, the air becomes thinner. Therefore, the temperature in the troposphere also decreases with the height in response. as seen in the picture. As one climbs higher, the temperature drops from an average around 17 degrees centigrade at the Earth's surface to minus 51 degrees centigrade at the top of the troposphere called tropopause. The first layer of the Earth atmosphere, troposphere, is followed by the stratosphere. This is the second atmospheric layer above the troposphere. The stratosphere extends around 50 km down to anywhere from 4 to 12 km above the Earth's surface. It contains 19% of the total atmospheric mass. In this region, the temperature increases with height. Heat is produced in the process of the formation of ozone, and this heat is responsible for temperature increases from an average minus 51 degrees centigrade at tropopause to a maximum of about minus 15 degrees centigrade at the top of the stratosphere. This increase in temperature with height means warmer air is located above cooler air. This prevents convection as there is no upward vertical movement of the gases. As such, the location of the bottom of this layer is readily seen by the anvil-shaped tops of the cumulonimbus clouds. The mesosphere is the coldest layer of Earth's atmosphere, located right above the stratosphere. The mesosphere is the first line of defense from bodies entering the atmosphere. Meteors begins to burn up upon entering the mesosphere. Mesosphere and thermosphere together contain 0.1% of total mass of Earth's atmosphere. However, 99.99% of the Earth's atmosphere is below the thermosphere. The transition boundary which separates the mesosphere from the stratosphere is called stratopause. Mesosphere extends from 50 km above Earth's surface to 85 km. Temperature decreases with the height in mesosphere. Thermosphere located above 85 km and extended up to 500 km. Temperature increases with height in thermosphere, and all ionization activity took place in this layer only. In this layer occurs molecular ionization due to ultraviolet radiation, gamma rays and X-rays of the sun. Due to this ionization, temperature of this layer sometimes as high as 2000 degrees centigrade. But it is difficult to measure the temperature of this layer accurately because of very thin atmosphere. In this layer, the meteorite disintegrate as soon as they touch the air.